as part of British Science Week. This is one of many sessions being put on by the OU Faculty of STEM from the Open University. The Faculty of STEM is made up of 4 schools, as well as the Knowledge Media Institute. And today you have 2 speakers from the School of Maths and Statistics. So, hello, my name is Charlotte Webb and I'm a lecturer in maths education.
Hi, I'm Rebecca Rosenberg. I'm also a lecturer in maths education. Our session today is about, is it magic or is it maths? And one of the things we want to talk about is looking at some sometimes well-known magic tricks that actually have a mathematical structure to them. We want to challenge the stereotype that maths is kind of there to trick you or is just made up and rules come out of thin air. So we're going to unpick some of these tricks and have a look at the structure behind them and what makes them work.
Okay, so our first trick, let's have a look. So everybody that's here today, you've got a bit of a challenge, okay? We'd like you to think of a number. It can be any number you like. I think for ease of calculation, we're going to ask for a whole number. If you can think of any whole number and then add 10 to it, multiply the answer you get from that calculation with the number you first started with, so the number you first thought of. Then add 25 to your answer and then take the square root. And what we're going to do is we're going to try and guess what your first number was based on your answer. So if you, as soon as you've calculated it, if you can put your answer into the chat box, then we will try and guess and work out what your start number was. So, so you do this calculation, any number, any whole number, add 10, multiply the answer by the number you first started with, add 25, and then square root it. So you can use a calculator if you want. There's no sort of test here on your arithmetic skills. You can do it in your head, and hopefully soon we should get some answers and we can try and see if we get your start number right correctly. So have we got any yet, Rebecca?
Yeah, we've got quite a few answers already. We've got Beth, who has said 32.
Okay, so 32. So I think, Beth, you started with 27. Let's see if we're right.
Let us know if we're right. Yes, she says.
Okay, perfect. Can we have another couple, Rebecca?
Kat says 12 and Kat says 9.
Okay, so Kat says 9. So I think, Kat, your answer was 4 to start with. And was the other one 12, did you say, Rebecca?
Yeah.
So 12, I think you must have started with 7. I didn't catch the name for that one, sorry.
That was Kurt, and someone else has said 12 as well. John, yes. We've got some yeses. Oh, wow.
Excellent. Okay, so hopefully you're convinced by our magic skills now. We've done a couple of those. The challenge for you now is to think about how we did it, okay? So there's quite a bit of a clue with looking at what you had to do to get your answer. But think about whether you can work out what we did. So the challenge to see whether you know what we did without sort of explaining it in the chat box is to ask you to do the trick back to us, okay? So we are going to tell you what our final number is, okay? So the final number is going to be 17, okay? So if the final number is 17, what number was I thinking of in the first place? So if the final number is 17, what number were we thinking of?
We've got a few answers already.
Has anybody managed to have a go?
We've got some people have said 12 already.
Okay, lots of people saying 12. Any other answers?
Not as yet.
Okay, it sounds like you've worked out the magic trick. So how does it work? Perhaps if you think you can explain it, you could add it into your chat box, into the chat box. And I think we're going to try and work it out together and unpick it. So if you haven't been able to work out what our starting number was, don't worry, we're going to go through exactly what we did and how we worked it out. And I think I'm going to hand over in a moment to Rebecca to kind of go through what we did. So the starting number I started with was 12. So well done, magicians, you've worked it out. Now, why is it? Why does that work? How did you know that it was 12?
Okay, so one of the ways of solving these think of a number kind of problems is to work backwards. And so that's to start at the end and do the inverse operations, working backwards or up to the top of the list to get to the number that we started with. So we could say, all right, well, I started with 17. And I'm working backwards, so I need to do the opposite of taking the square root. So that's squaring. So I'm going to square 17, and that will give me 289. I didn't do that in my head just now really quickly. I already had it written down. Okay, and then add 25 to your answer was the penultimate step. So the inverse of that, working backwards, doing the inverse in reverse, is subtract 5. So that'll give me 284. And then I've got to multiply that answer by the number that I first thought of. So I need to do the inverse of multiply. I'm working backwards, so that's divide. But I don't know what the number that we first thought of was. So I've just got to sort of divide by something n, and I don't know what that is, so I'm just going to leave it as that, just an n representing my unknown number, and then add 10. So the inverse of that is subtract 10, and that should give me the number I first thought of, which I'd called n. And it's a little bit complicated like this. It looks a bit weird. So I've worked backwards and I've done the sort of undone that process of think of a number, but it's not given me the starting number straight away. If I rearrange this, I'd get a quadratic, which I could use factorizing or the quadratic formula to solve to find out the value of n. But we didn't do that really quickly in our heads, and nor did you when you came up with the answer 12. So there's something else going on.
Yeah, exactly. I've just, not to nitpick you, but I've just noticed one little thing, which is I think that should be 25 and that should be 64. But otherwise, perfect.
Oh,
yeah. Yes, so basically, we didn't do that. We didn't solve a quadratic really quickly every time you gave us an answer. Certainly not. Mathematicians generally like to try and find the easiest way to do things. So we didn't do that. So we didn't work backwards every single time. We had a bit of a sneaky trick to get there more quickly. And if you think you know what that is, please do add in the chat box. I can see the chat box is very lively. So perhaps Rebecca can let us know if anybody has sort of figured out what we're doing. But we're going to run through how we did it. And we kind of thought of this whole process as a number of steps, and we wanted to kind of cheat and see whether we could do all of those steps in one go, sort of jump to the end, so that we'd then be able to undo your work and kind of work backwards and work out what your number was. So in a similar way to Rebecca just sort of indicated there, we've got a number that we don't know about. We've got this number that we've thought of. It could be in a thought bubble, or we could call it n. So we're going to call it n to have something to work with. Once we start using algebra, we've got something to manipulate. So sometimes people get a bit scared of using algebra and using letters, but actually it's just giving us something that we can actually operate with. If we had a question mark there, it would be exactly the same thing, but it's just easier to use a letter. We can sort of sort it out a bit easier when we've got a letter. So just going to run through forwards this time instead of backwards and just see what happens. So think of a number, add 10, that's quite straightforward. And we're going to multiply by the number that we first thought of, which was n. Now, depending on what you're trying to do, you might want to leave it in brackets. I'm going to expand this out and multiply the brackets out so that I get n squared plus 10n. The reason for that will come clear later. Then I've got to add 25 to my answer. So that gives me, again, a quadratic. So I have got a quadratic here, but hopefully we're going to be able to tidy it up and make it a little bit simpler. So the next step is to take the square root. Now, taking the square root of something in that form, or even in the form n brackets n plus 10 bracket plus 25, which we would have had if we hadn't expanded, looks a bit tricky. But actually, you might have spotted the same thing that we've spotted, which is that we've got n squared here and we've got 25 here, which is a square number as well. And any of you that have seen factorizing or expanding quadratics will sort of notice that we've got something like an n squared, and a 5 squared. So we can try that. And actually n plus 5 all squared will give us this expression, because you end up with n squared giving you the first term, you've got 5 squared giving you the last term, and you also end up with 2 lots of 5 times n. So you end up with 5 times n and then 5 times n again, which gives you the 10n. And now, because we've rewritten this as a square, what happens when you square root a square? Well, it cancels out, doesn't it? We square root a square number, we get back to the number we started with. So we've ended up with something squared, square rooted. So we end up with that something, which is just n plus 5. Now you can see very easily how we managed to get your answer. We didn't solve a quadratic every time. We were simply taking away 5. And I think probably that is what a lot of you were doing when you got from 17 to 12. Does anybody confirm that in the chat box? Is that what other people did as well, Rebecca?
Yeah, and we've had Beth who wrote out something very similar, but using X, which obviously it doesn't matter which letter you use, N or X would be fine to represent some unknown value. Yes, so we've got a lot of people confirming that that was what they did.
Brilliant. And the great thing about these think of a number questions is you can do them in all kinds of different ways. You can change the type of calculations you want to use depending on who you're doing it with. So if you're doing it with sort of young children, you can make them quite simple and sort of still manage to go through it with them and they can understand it. You can make them much more complicated than this if you like. And the trick is to try and make it really difficult to see what the undoing is. So here what we've done is you can see that we multiplied by the same number in order to get the n squared, and then we square rooted to get rid of that. So it was hidden a little bit because we didn't use the word square and square root. We tried to hide it a little bit, but you could make one even more complicated where you've hidden it even better so that it's really difficult for the person to see how you did it. So that's our first trick and possibly our most straightforward one. I think we're going to go on to another trick now.
Yes, and thank you for the people who also, as well as Charlotte, noticed that I should have taken away 25. Sorry about that. Okay, the second trick is about birthdays. So what I'd like you to do is have a look at cards 0, 1, 2, 3, and 4, and have a look at which cards have the day you were born written on them. So it might appear on more than one card. And once you've found which cards have the day you were born written on them, type into the chat box. So if it's on cards 3, 1, and 0, just type 3, 1, and 0. And I will be able to tell you what day your birthday is on, hopefully. And if you'd like, also try and figure out how I'm doing this.
So should I have a go with my birthday, Rebecca, and see if you can work out what my birthday is?
Well, we've already got some people actually.
We've already got some people. Excellent. Okay.
Yeah. So Anita's birthday, oh, it's disappearing again, is on card 2. So your birthday is on the 4th. Oh, they're moving very quickly.
Okay, Rebecca, I can give you some answer from the chat box. So you concentrate on the cards. So Ruben is, oh, it's just moved away, so I'm gonna have to move someone else. Christabel is on the 4th and the 1st card. So could you please work out Christabel's birthday, please?
The 18th.
18th. So Christabel's the 18th. I'm going to write it down so I don't lose it now. Okay. Elliot has got on the 0, the 1, the 3, and the 4 card.
Okay. That would be on the 27th.
Okay, let's write that down and see whether Elliot can confirm. Okay, we've got a yeah in the chat box. Okay, Ruben, 0, 1, 2, 3.
Ooh. Would that be on the 15th?
Okay, let's have a look. Ruben, is that the 15th? Yes, it looks like that's correct. Well done. Okay, Kurt is on 1 and 3.
The 10th?
And Kurt, is it the 10th? Yes, excellent. Okay, and also apparently Ruben is eight years old, I presume, and he's amazed by the magic. So well done. Thank you, Rebecca. And we're right about Christabel, and we're right about Kurt as well. So excellent. Okay, so are we convinced now that Rebecca's doing some sort of magic or some sort of maths here to work it out? Has anybody got any idea what it might be to do with? You can keep thinking about it and adding to the chat box. Okay, so shall I click ahead?
So let's, we're going to move away from these birthday cards for a minute and have a look at binary. Some of you might have already noticed something going on with powers of 2 or 16 and 8 and 4. I can see Colin said add the numbers in the top left-hand corner of each card, and you're onto something there, but that doesn't quite explain how we find out which cards to notice in the first place. So let's have a look. Some of you might already know how binary works, but I'm just going to show you a very quick run through so that we can look back at the birthday cards and see what's going on. So binary is a way of writing numbers in using just base 2. So that's powers of 2. When we write our numbers as we ordinarily do using numerals, we use base 10. So we've got a units column, a tens column, a hundreds column, a thousands column, and so on. In binary, we're using base 2. So we've got a units column, which is 2 to the power of 0. That's 1. A 2's column, 2 to the power of 1, which is 2. A 4's column, or 2 to the power of 2, which is 4, and 8, and 16. Oh, let me just write that 16 a bit nicer. So when we write numbers in binary, all it does is give us a string of 1s or 0s to tell us whether that power of 2 is included. So for this first number, we just have 2 to the power of 1. So that number there is a number 2. In the second one, 1, 1, 1, 1, 1. Every column is included. So we've got 1 plus 2 plus 4 plus 8 plus 16, which is 31. Here we've got 1, 0, 0, 1, 1. So that's 16 plus 2 plus 1, which is 19. And 0, 0, 1, 0, 1, which is just a 4 plus 1. So that's 5. So that's how binary works. And now that we all know that, let's move back and have a look at those cards again. So I'm going to tell you my birthday is, oh, let me just clear those, sorry. So my birthday appears on cards 2, 4, and 1. So can anyone tell me what day my birthday is on? Someone said the 26th, the 23rd, or the 7th. We've got lots of different answers.
Yeah, we've got the 22nd. Yeah, Christopher says 23. Beth says 19. So what some people might be doing is looking for numbers that appear on more than one card as a sort of clue.
And 23 does appear on 4, 2, and 1, but it also appears on card 0.
Mm-hmm.
And I didn't say card 0. I think if could you just move on and show the?
Yeah, of course. Yeah. So just seeing everybody's lovely answers.
Loads of great contributions. Some of you, or quite a lot of you actually, have got it right. It is the 22nd, and it was the 22nd of January, so I had a lockdown birthday, like almost everyone. And here we've got the powers of 2 above each card. So card 4 represents 2 to the power of 4, card 3 is 2 cubed, card 2 is 2 squared, card 1 is 2, and card 0 is 2 to the power of 0. It's a bit weird to have a card 0, but we needed it so that we could work in binary. And my birthday, 22, written in binary is 10110. And each card is given a 1 in its column or a 1 in its place value system if the number 22 appears on that card. And that's why I think it was Colin who said add the numbers in the top corner. And yes, the powers of 2 do appear in the top corner of each card, but the way that we find the cards, find the columns that have a 1 in, is by looking further down the cards and seeing which number it appears on. So the way this works is each number from 1 to 31 only appears on the card if it can be made from those powers of 2. I'm just pausing so that, because I know there's a bit of a delay with some of the other streamings, and there's quite a lot going on. I was just saying
well done to lots of people who got it right. So I'm wondering whether any of those used what you're talking about, or whether they noticed something else about the cards. Interested to know how you knew it was 22. If you did get that, how did you get it? And yeah, we've got some people who are engaging through YouTube and Facebook and getting those comments through as well. So great to see you all engaging. So is there a quick way of doing this, Rebecca? Because as we said in the last trick, we like to do these, we like to show you how they work, but we also kind of like a quick way of being able to work out the answer. When somebody tells you their cards, how do you quickly get to the answer of their birthday?
So I think someone has or actually just said it in binary. So if my birthday was on cards 4, 2, and 1, I just wrote a 1 in those columns for 2 to the 4, 2 to the 2, and 2 to the 1, and then a 0 in the other columns to show that there was no power of 2 represented, that power of 2 represented in the birthday number. And so if we have a look at the number 6, for example, when we write the number 6 in binary, it's the highest power of 2 in the number 6 is 4, and we then add 2. So 4 plus 2 is 6, and that's 2 squared plus 2 to the power of 1. So the number 6 only appears on cards 2 and card 1. And in fact, the highest power of 2 is that first number, and that's where that these powers of 2 in the top left corners come in.
So we've got a little bit of a quick way of getting it, haven't we? If we just add up those numbers in the top left, as you said. So for your birthday, you just needed to add up 16, 4, and 2. Is that right? Yeah.
That's right.
Yeah. So if you're doing this trick with your friends and family, you can explain the maths behind it, but you can amaze them by very quickly finding their birthday just by adding up the top left number in each card. Oops. So yeah, a lovely trick to share with your family. And at the end of this session, we're going to give you the opportunity to have these slides if you would like them, so that you can take these cards away. Or alternatively, you can Google binary birthday and binary birthday trick and find these cards online.
Okay, I think we're going to move on to trick number 3. We're zooming through them.
Yeah.
Okay, so trick number 3 is about predicting the future. earlier today, I wrote down a number on and put it inside this envelope. And I'm going to try and hold this envelope up the whole time so that you can see that there's no cheating going on. What we're going to do is write down 5 4-digit numbers. And my prediction was that they would all add up to the number that I wrote down on this envelope earlier. So you can contribute as well, and I'll keep an eye on the chat. Charlotte, I think you're going to scribe these numbers. Thank you. But I'm going to start. So the first number that I would like to put in is 8,104. And then can all of you please contribute some 4-digit numbers, and we'll take it in turns. Okay, Joshua's done one straight away, 2001. Okay, and I'll go next and choose 7,998. Ruben's got one, 3,205. And oh, this is the 5th one, so I'll say the 5th one, which is let's say 6,794. Okay, so
we can get some help now from the audience. We need to add those 5 numbers up. So let's see if you can add all of those 5 4-digit numbers up and share the answer with us in the chat box. So again, you can do it however you like. You can do it in your head, you can write it out, you can do it on a calculator. Let's see whether we all get the same answer, and then we can see whether Rebecca's number in her envelope matches what we get. And see if her trick, she is really a magician and can predict the future. Okay, so lots and lots of people writing the same number. I'm going to write that on the screen. So Joshua, Beth, Kurt, lots of people saying 28,102. Let's give everybody on YouTube a second to catch up and see whether we've got any different answers, but it looks like there's lots of the same, 28,102. Okay,
are we ready for the big reveal? Can't remember what I wrote now. Hope it's correct. Dun, 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 dun.
Wow.
8,102.
Amazing. Whoa. Okay, well, I want to see whether I can keep up with this, magic ability that you've got. So I've done the same thing. My envelope has been decorated as well with some stars, and it's sealed. So I've got an envelope as well, which has a number in it, and we're going to ask the audience again to give some numbers, and I'm going to start with a number. So I'm going to start with the 4-digit number. I'm going to start with 4,957. So can we have an answer number from the chat box, please?
Okay, we've got Christopher says 5,103.
Okay. And I think it's my turn to have a go. So I'm going to pick a number. I'm going to pick 4,896. Okay, let's have another random number from the chat box.
Okay, we've got Kaz with 1,794.
Okay, and we need one more number, so I'm going to pick another random number. So I'm going to pick 8,205. Okay, so let's see whether everybody in the audience, I'm still holding my envelope here, so I haven't moved it away, can add up that number for us. So we've got 5 4-digit numbers. Are you able to add them up for us, and we'll see whether the answer you get is in my envelope. And whilst you're adding that up, you might be thinking about how we did it, or whether this was a fair challenge, whether you noticed anything about the way that the numbers were chosen or anything like that. So have a think about how you think this might work. This magic maths trick works.
We didn't get to it in time, but Brenda contributed the number 1000 as the 4-digit number. So she might be onto something about what's been going on. And that was a little test.
Might have been, or she might have just liked that number.
maybe it's just a good number. So we've got some contributions already for the total. So people saying 24,995.
See whether we get any other answers. So I think that you might be a bit critical of our sort of method of choosing numbers, about who got to choose numbers and when. I wonder if anybody thinks anything suspicious was going on.
Okay, we've got a few people saying 24,955.
Okay,
which is also what I got actually when I added them up on my calculator.
Okay, can you say that again for me, please, and I'll write it up?
24955.
24,955. Okay, so let's have a look, and then I think we've got somebody might have an idea of how it's working in the chat box. So I've got my envelope, and I'm not going to do it as neatly as Rebecca because I actually taped mine up. And
you're just more thorough.
Anyway, I've got a nice green. This is my craft box getting accessed. Okay, so can you see that?
24,955.
Okay,
you can predict the future too.
Excellent. So we did manage to guess the right answer. How did we do it? Beth's got an idea. She's saying something about the answers adding up to 9999. Can anybody else say anything more about that, or what that's got to do with our answer? This is another trick you can do with your friends and family and amaze them. So why is 9999 or 9,999 important?
And Christopher said that you chose numbers to make it work at the start and halfway through. So yeah, we had a lot of control over what was going on, didn't we? We chose the start number and the middle number and the end number.
Yeah. Yeah, so we both chose the first number, and we both chose the third number, and we both chose the fifth number. So somebody said you chose the numbers from halfway. We also chose the answers from the suggestions. You're right. Although I do have to say we did just pick any numbers from the chat box. That wasn't a particular choice. That was just whatever came up. But we could have cherry picked what we wanted. I think somebody said something about we chose the numbers to make it work. So how did we respond to the answers that were given? We chose an answer from the chat box, and then we followed it with our own answer. Can anybody notice anything about that? I think Beth's already on to us, but maybe somebody else might be able to see what we did when we chose our numbers. What do you notice about the numbers that we chose after the numbers you chose? You might also notice something about the starting number that we chose and the answers. That's another place to look for a clue. Okay, well, a couple of people are starting to get the same idea, I think, as Beth here, which is something about it adding up to 9999. So perhaps we can go through why this problem works. Let's have a look together.
Okay, so let's choose another starting number. So let's say that this morning we'd have written down 29,654, and that was the hidden number. The way that we then worked out our first number to write down, that first 4-digit number, was first subtracting 20,000 and then adding 2.
Yeah, and somebody has noticed that in the chat box, actually.
Oh, well done.
Somebody, Kaz, said that the last 4 digits are the same, but 2 less. So exactly what you just said. So the last 4 digits of the answer you wrote in your envelope are the same as the number we started with, but 2 less. Yeah, that's well spotted.
Absolutely. And so if we were to, let's just have a look at another example. So with this one, our starting number would be, or our first 4-digit number would be our hidden number, subtract 20,000 and then add 2. And the reason for that is exactly related to the fact which people have been saying, which you've noticed, is that the numbers we chose added up to 9,999. So we had a predetermined hidden number, and that gave us, by subtracting 20,000 and adding 2, that gave us the number that we first start with. And then if you choose any other number, let's say 1,000, which we didn't have time to include, but would have made it perhaps a bit obvious what was going on, we just need to make sure that whatever number we put next, the corresponding digits in each units, tens, hundreds, and thousands column all added up to 9999. And we do that twice. So if we have 9,000, 9,000 is not a good one, is it? Because then that first number there would be 0 on the number we'd have had to choose, and that then wouldn't be a 3-digit number. So none of you actually said a number that started with 9,000 that we saw, but if you had have done, that would be where we'd have done some cherry picking and not picked a number that started with 9,000 or started with a 9, because it would have given the game away. So yeah, let's say 2, 3, 4, and 5. And we would have then chosen 7, 6, 5, 4. Again, giving another pair that adds to 9,999. And these two together add to give our almost 20,000, 20,000 minus 2. The reason we've written it like that is to make it really sort of quick to calculate and easy to see what's going on, and also to see the link between the hidden number and the first 4-digit number. So you don't necessarily have to choose pairs of numbers that add up to 9,999, but it just makes it a bit easier to calculate. So you could experiment with it, try and maybe find some other number that they add up to that might make it a little bit less obvious as what's going on, especially with this kind of number here, where you can see quite easily what's going on. So that's how it's done.
Lovely, thank you, and well done to all those people who spotted what was going on, that we were adding up to 9,999, and that gave us a lovely trick to find our final number with our starting number. So well done, everybody, for getting that. We're going to move to a slightly different trick now, which requires you to do some more calculations. Okay, so before you start, I'd like you to open the link, which I think we can pop into the chat box as
yeah,
well.
I'm just putting it in now.
Rebecca's putting it into the chat box, and the link will basically take you to an online book. So if we were doing this in person, I'd have a physical book that we could look at and give to somebody in the audience. But as we're doing this online, we're going to have an online version of the book. And what I would like you to do is to calculate, is to find a word basically. And the way you're going to do that is you're going to calculate a 4-digit number, and the first 3 digits of that 4-digit number is going to be the page number, and the 4th digit of that 4-digit number is going to be the word on that page. Okay, so the way that you're going to get that 4-digit number is by doing a series of calculations. Okay, so what you need to do is think of a 3-digit number. Now, there is one sort of rule about this. The first digit has to be at least there has to be a difference of more than 1 between the first and last digit. So for example, you could have 5 as the first digit and 3 as the last digit, but you couldn't have 5 and 4. Okay, so you could have like 503, or you could have 462. That would be okay. Any 3-digit number where the first digit and the last digit differ by more than 1. Okay, then what you're going to do, and I'll just do this to show you. You're going to start, so say I had the number I just started with, 462. Okay, then you're going to reverse the digits. That's 264. Okay, you're going to subtract them. That's why it's better to start with a number where the first digit is bigger than the last digit, otherwise you'll have to swap them over. So subtract those, you're going to get an answer, a 3-digit number answer. When you get that answer, you're going to reverse those digits, and then you're going to add those 2 numbers up. Okay, so you get your answer from your subtraction, and then you reverse the digits of that answer, and you add those 2 numbers up. That will give you a 4-digit number, which gives you your page number and your word number. Okay, the first 3 digits is going to be your page number, and the last digit is going to be your word number. Okay, so for example, if you had the number 2273, then you would go to page 227 and you would count the 3rd word on the page. Okay, now we do want to show you the book, just to show you what it looks like, but I also don't want to lose these calculations off the board. So we might just show you very quickly and then come back to these calculations, just to show you what the book looks like. Okay, so you can see here, we've got the Alice's Wonderland. If Rebecca, if you flick a few pages along, we've got Alice's Adventures in Wonderland. If you flick a few pages along, you'll see that the page numbers don't quite match up with the top. So we're kind of looking for the page numbers in the book itself. So for example, here, it'd be page 4 and page 5. Okay, so even though it says 16 at the top, the answer you get, we'd like you to find it on the actual page itself. So that might involve a little bit of flicking. Okay, and then you're going to look for the word. So say it's the 6th word, then you're going to count all the words on the page starting from the top and find that 6th word. Okay, and then you can keep a note of it. And I'm going to choose somebody randomly to try and guess what their word is. Okay, we'll give you a few moments. If we go back to the slides. Okay, here we go. Then you can see the calculations. Okay, so you're going to follow these calculations, find your page number, find the word on your page, and then when you've done it, I don't want you to tell me what the word is because that's the trick, but if you could just say in the chat box, got my word, or finished, or something like that, and then I'll know who we can pick from the chat box to be our volunteer. So just to run through it again, you're thinking of a 3-digit number where the first digit is larger than the last digit by more than 1. So there's at least a difference of 2 between them. And you're going to reverse those digits, subtract them, reverse the answer, and add those 2 together. Okay, so you should end up with 4 3-digit numbers in your calculations, and then the final answer will be a 4-digit number. That will give you your page number and your word number. A little bit of work to get to the actual answer here. So for example, if this was your answer, then your page number would be 200 and your word number would be 9. Okay, so as soon as you've got your number, you can go to the link and find your word. And as soon as you've got your word, if you can just say into the chat box, got it, or something like that, so we know.
Yeah, don't give us your actual word because Charlotte is going to predict what the word is.
Yeah, exactly. We don't want to give it away. But you might want to think about, if you have managed to do it and you've got your word ready, I see Beth's got her word ready, then if you have got it ready, you might want to start thinking about what you think might be going on here. Doing some predictions about what we're doing here to get our answer. Just give everybody a little bit of time to calculate. This is another really good trick to do with people. It's actually a really famous trick. You can Google it afterwards as a famous book trick. But it's a really good one to use in person because you can have a book, as long as you've been able to look at the book yourself and the person who's you're tricking has is able to look at the book. And it's quite a nice one to do in person. It can be quite impressive. So it's quite a nice thing. So we've got Christopher and Ruben and Beth have got it. Okay, so shall we see whether I can guess what Beth's word is? Okay, so Beth, can you just confirm to me in the chat box that you did use the page number in the book, not on the top of the PDF? Okay, and that you started from the first word on the page, so including sort of any titles or anything that was on the top of the page. Just to check that we're going along the right lines. Okay, in which case I think that your word is subject. So can you tell me, Beth, if that was your word? Yes, excellent. Okay, and I can see that Christopher and Ruben didn't include the title, but I think I can guess what their word is if they didn't include the title. I think that Christopher and Ruben's word is interrupted. Let's see. They didn't include the title. I think that they would have got the word interrupted. Wow, we've got a wow, excellent. Okay, okay. Now, I only had 2 volunteers there, but I'm hoping that a few of you are sort of thinking, hold on a moment, I got that word as well. So what did we do? How did we do it? Has anybody got any thoughts about how we were able to guess both Beth and Christopher and Ruben's word? Well, I'll give you a bit of a clue. Okay, so I'm gonna move on the slides. Hopefully you've all had time to do the calculations. So Beth said something really interesting, which I think that we're going to come to as well, which is that she said, I did it a few different times with a few different numbers and I always got the same answer. So I think that if you use the page number in the book, you got all page 108. I think all of you got page 108. I think that if you included the title, then the 9th word, I think you're all looking for the 9th word. And I think that if you using the title, you got subject. And if you weren't using the title, you got interrupted. So I think you were all looking for the 108th page and the 9th number. So why? How did you all end up with the same number? Okay, I also did a little extra option in case anybody did 108 in the actual PDF. If anybody did that, then I think you would have either got the word some or the. So how did we do it? Well, I think that Beth's made a really good point here, which is that whatever happens, whichever answer number you start with, you always end up with 108 and 9 as your numbers. Okay, you always end up with 1089 as your answer. Now, why is it? Christopher and Ruben have said it's something to do with reversing the numbers, something to do with adding and subtracting the numbers. Well, there was a rule that I put in place here, and the reason for that is because if you had ended up with a number where there was only a difference of 1, this rule wouldn't quite have worked. And I'm going to show you why. Okay, so if we start with the example, for example here, 542. So it's like the one on the left, but instead we've got 544. Okay, so that there's a difference of 1. Okay, if we'd have turned that around and done the subtraction, we would have ended up with, the first answer would have been 99, okay? There's lots of 9s in today's session. I feel like 9 is a really special number here. And the reason why I didn't want this to happen is because then when you did the swapping over of reversing digits, some of you might have done this. And if you'd have done that, then great, it would have worked. But some of you might have thought, no, that's not really a number. 099 isn't a number, 99 is a number. So you might have turned it around and just put 99 and 99 here. And then my trick wouldn't have worked. So that's why I told you not to do that. But what you will have noticed is that in all these examples on the board, these numbers here crop up more than once, okay? So here, the difference between 3 and 1 is 2, and the first answer is 198. Here, the difference between 8 and 6 is 2, and the first answer is 198. That's not a coincidence. It's also not a coincidence that 198 is 2 lots of 99. And 3 lots of 99 gives us 297, which is what we get if we have 2 digits which differ by 3, okay? So what you could actually do, like Beth, is you could try lots of different examples. You could try one with the difference of 2, which always gives you 198 as your answer after subtraction. You could try one with the difference of 3, which always gives you 297. You could try one with the difference of 4, which gives you 396, which again is now 4 times 99. And you could carry on as like so. So all of the answers are going to be multiples of 99. And when you reverse the digits of all of these first answers, you always end up with 1089. And we can actually prove this algebraically. You don't need to prove it algebraically. You could do it by a proof by exhaustion, which is what I've kind of been showing you, where you try all the options. But you can do is show this algebraically. And the way you can do that is by thinking about how these numbers are structured. So at the beginning of the session, Rebecca was talking about the structure of numbers and how you can use that to help you work things out. Here we've got 541. We can think about that as, it's a bit like partitioning when you think about place value. We can think of that as like 500 plus 40 plus 1. Or we can think of it as something in the hundreds column, something in the tens column, and something in the units column. Okay, so we can actually write a 3-digit number in algebra. Okay, we can then reverse those digits. Basically means that where the 5 was the first digit, now it's the last digit. So the A, instead of being the first digit, is the last digit. We can simplify this and we can end up with an expression which is 99A minus 99C. Now, you can prove this algebraically by going through for every single option, but one way of doing it is to just say, okay, well, if I know that A is always 2 more than C, if I know that I've got a difference of 2, then I can substitute that in, and I end up with always, whenever there's a difference of 2, I always end up with my first answer being 198. Which gives us the answer on the previous page, which always gives us 1089. So I'm going to leave that a little bit open with you to try and convince yourself. So we haven't fully explained it in a way that you might, some of you might be convinced, but others of you might want to play around a little bit more and explore it. So you could try it by trying all the different options of combinations. So whether the first digit is 2, 3, or 4, 5, or 6 more than the last digit. You could try it for all those options and convince yourself. You could try an algebraic proof if you feel that you would like to. Hopefully you can use this trick to impress some of your friends and families. I'm just going to see if there's somebody said something in the chat box. Yeah, okay, we're very willing to share the slides at the end. I'm going to put our email addresses at the end and you can let us know and we will share the slides with you. So the reason why I chose this particular trick, as well as it being a nice thing to do with a book, is that this number 1089 is actually really quite a special number. So I've shown you that it's all to do with powers of 9, multiples of 99, but there's loads of other properties of this number. So I just wanted to share a few with you. I just kind of wanted to finish this session by showing you some nice things about this number, because I think it's quite a magical number. So 1089 is a square number. It's actually 33 squared. So you probably don't know your square numbers up to 33 squared. It's also the product of 2 square numbers. It's the product of 3 squared and 11 squared. it's also a really nice number because it's the first reverse digit number. So what that means is if you take 1089 and you write it in reverse, all these reversing going on today, it's kind of a common theme. If you write this in reverse, so instead of 1089, it will be 9801 in reverse, okay? Then that number is actually divisible by 1089. So it's the first number of its kind that does that. And there's actually only 4 of them. There's only 4 4-digit numbers which you can reverse and then they're divisible. So that's quite a nice fact. It's also a nonagon number, so a bit like a square number or a triangle number, but with a nonagon, so 9-sided shape. And there's also loads of other patterns. So if you look at the reason why it works in this trick really is because there's loads of patterns with the 9s times table and the 99 being a factor. So here we can see that 1 times 1089 is a reverse digit of 9 times 1089, and 2 times 1089 is the reverse digit of 8 times 1089. So you can actually spend a whole day exploring this number, and I hope that you will. And just going back to Rebecca's trick, I think it's nice to also see it in binary. So yes, the magic number 1089. I hope that you go away and explore this number a little bit more and see what else you can find out. And if you do find anything out, we would love you to get in touch with us and let us know what you found out, either one of our emails or through Twitter, which I think can be shared in the chat box on Twitter.
So thank you so much. That's the end of our session. If you've got any questions, we have run a little bit over, but if you've got any questions that you'd like to ask us now, then please feel free to ask in the chat box. Or if you've got to dash off, then yeah, our email addresses are there, so do get in touch if you'd like. And you should also notice in chat that if you'd like a copy of the slides, then there's an email address, stem-communications@open.ac.uk, that you can email as well. We just also wanted to mention we've got a couple of free courses. So if you liked this session, there's a course that's on OpenLearn from the Open University called Perplex. There's a little image of it there, and that's got loads of maths puzzles on that you can go and explore. On OpenLearn as well is a teaching maths course, and that's a free course for anyone who's interested in learning a little bit more about some themes and ideas behind secondary maths education, which is the department that we work in. And some of the things we've spoken about are included there. So stuff to do with the structure of numbers and doing and undoing, and the idea of becoming convinced and things like that. So you can read more about that in these free courses as well. So yeah, do let us know if you've got any questions at all. And well done to everyone, because you've done 4 tricks and everyone's contributed really nicely. So thanks for getting involved as well.
Glad to see that lots of you have enjoyed it, and I hope that you do take these tricks away. As Rebecca said, if you like the slides, you can get access to those, and then you can use these tricks on all your friends and family and impress them with your maths and your magic skills. And do let us know if you do manage to do any of them and you want to share a little story with us. We'd love to hear from you. So thank you very, very much.